Alright, so we're almost there. I got one more homework after this one, and we'll be done for this course. And let's go ahead and start with this problem. So, the first thing we want to consider is the maximum amplitude of the voltage. Now, if you go to the equation right here, it's given. There is 40 volts as a peak amplitude, because as you know, cosine swings between -1 and 1. So you multiply -1 and 1 times 40, you get 40. So the maximum amplitude is 40 volts. The frequency in hertz we can get from the angular frequency right here. So you make the angular frequency divided by 2 pi. Let me just put this here. Say that, I'll just leave it as omega. So omega over 2 pi equals f. Well, if we have 100 pi divided by 2 pi, that's 50 hertz. Frequency in radians per second, it's actually given right here. It's 100 pi radian per second. So in 1 second, there's 100 or 50 complete revolutions on a circle. Phase angle in radian. Well, the phase angle is 60 degrees. Turning that into radian, it's going to be pi over 3. Phase angle, phase angle in degrees is also here too. Yeah, so here's phase angle in degrees, phase angle in radian, and the period in milliseconds. So now we got to do a little bit of arithmetic. And the way we'll do that is we want to find out, we'll take the frequency, go on in seconds, right? So the frequency is going to be, the period, sorry. We already know the frequency. It's going to be 1 over f. So 1 over 50 hertz is going to be 20 milliseconds. Now I want to find the first time after t equals 0 that the voltage equals -40. So basically we want to find out where cosine is negative, or -1. Now if you remember your unit circle, cosine is going to be negative at 180 degrees. So if we figure out what value for t makes the argument of cosine 180 degrees, then we'll know what time after t equals 0 that equals -40. So you do that, well, if we know that pi radian is going to be that, and we have t plus pi over 3, that means t equals 2 pi over 3. Now, that's not in seconds, so to get that in seconds, we're going to divide it by the angular frequency. 2 pi over 3 divided by 100 pi is going to be 6.67 milliseconds. I don't know why I did the bar. Now, it also asked, what if the sinusoidal function shifted 10/3 of a millisecond to the right, then what's the expression for vt? So basically, our initial wave is going to look like that, and we're going to have a phase shift to move it this way. So to do this, all I got to do is modify the argument for cosine. So 40 cosine, and then we're going to have 100 pi t. But we're just going to subtract 10/3 of a millisecond from here. So 10/3 to -3. Include our phase angle. There you go. So the minimum number of milliseconds after that function shifted to the left. Oh yeah, okay, I almost misread it. So now we gotta find out the minimum number of seconds that shifting it to the left is going to make our function basically sine. So if you remember some trig stuff, trig identities, sine of t is going to be cosine of t minus 90 or pi over 2. The cosine and sine are orthogonal to each other, or in other words, they are in quadrature. And this becomes important for some other applications, but in this case, we're just using it to solve a math problem. So we're going to have 40 cosine of 100 pi t minus, let's call this t shift, plus our 60-degree phase angle. It's going to equal 40 sine of 100 pi t. So we're going to do 40 cosine of 100 pi minus 90 degrees. So basically we're trying to find out what kind of phase shift we need to make it like that. And we will do that as we will get the arc cosine of both of these, or even just look at the arguments because they're going to be the same. So we'll just pull the arguments out because they're the same overall outside function, and we'll solve for Ts equals 100 pi minus 90. So if we put everything together, just move the 150 to the other side and subtract the 100t from both sides. We're going to have 100 pi times the t shift equals 150 degrees. So since this is in radian, we can't go directly to degrees and get our phase angle, or not our phase angle, or our time shift. We already know our phase angle is going to be 150 degrees. So we need to find out what time shift will make that possible. So to do that, we're going to take, say, Ts equals 150 degrees divided by 100 pi radians. So 1 radian is 180 degrees, which means that the time shift required is 8.33 milliseconds. This problem, we have to graph a bunch of sinusoids. They're all based on 100 cosine omega t plus phi. Now, we're not given an angular frequency omega, so I picked omega equals 1 radian per second, just to make it easier to graph. And I'm not the best at graphing, so I went ahead and plotted these in Symbolab, but you can see kind of what's going on here. Now, we want to find out, based on the graph, if phi becomes more positive, then what's the relationship between the graphs in the left and right direction? Well, if you look at the graphs, you'll notice if the phase angle becomes positive, we're going to shift leftward, and vice versa for whenever phi goes down, becomes negative. And based on that, we'll be able to make the assumption that if the phase shift changes from 0 to negative 30 degrees, then we're going to be phase shifted. Say we had a waveform right here, and we phase shifted it by 30 degrees, it's going to move rightward in the graph. Say that this is a 30-degree phase shift. And this becomes important when you talk about reactance and capacitive and inductive reactance. In a case where the load is inductive, the current is going to lag the voltage. And for a capacitive load, the current is going to lead the voltage. And you can see that if you think about your equations for the components. Remember, ICT is C d VCT dt. Looking at that equation, it makes sense that the current is going to change more quickly than the voltage. In fact, if you integrate this, you'll see that it does. And the same thing for the inductor. The voltage drop across the inductor is going to be dilt dt. And you can see the current is going to lag the voltage. The voltage can change faster than the current can in the same amount of time. So it makes sense that our phase shifts would be like this. So this is the first time we're going to start doing any kind of math with phase vectors. Now, in case you don't remember, phase vectors are just like any other vector, but we do these with phase currents and steady states and all this business. We have magnitude and phase, and the magnitude is going to be m, and then there's going to be the j theta, that's our phase. And it's basically just a manipulation of the famous Euler identity. And let's go ahead and start by changing A into a phasor and then use that to combine the two. So we have a magnitude of 50 and a phase of 60 degrees plus magnitude of 100 with a phase of minus 30 degrees. That's going to translate to, if we take the cosine of, actually, just to make it more clear what I'm doing here, remember this is going to be cosine theta plus j sine of theta. And if we wanted to, we could say, here's the magnitude. So I'm going to do 50 times the cosine of 60 degrees is 1/2. Yeah, it's 1/2 plus j root 3 over 2, which is the sine of 60 degrees, times 50, plus root 3 over 2 times 100, which is the cosine of minus 30 degrees. Actually, yeah, it is. The sine is the negative one. So j is going to be negative 1/2 of 100. So combining those terms, if we use a calculator to do everything, our magnitude is going to be the real part of the complex number, or rather the legs of our triangle, so to speak. So we're going to basically finding m, and we have this projection, a and b. And the complex number is going to be in the form a plus jb. And the reason why we use j, in case you don't know, j is just the imaginary unit. You remember it being seen as I. But in this course and in many other courses we use j because it's harder to confuse j with I. And since I is used, or sorry, it's harder to confuse I with current, or J with current. Anyway, so our magnitude is going to be a complex number like this, and our phase is going to be the phase of, or sorry, the B over A. You can also think of it as the phase of one of them minus the phase of the other one if we were doing a ratio. But that's a topic for a different course. Anyway, so A is going to, or the M is going to end up being 111.8, and the phase is going to be minus 3.43 degrees. And in case that is confusing, because I didn't really show the step, all you gotta do is add these numbers up, add the real parts to the real parts, the complex parts to the complex parts, and you end up with an expression. It's going to look something like this: 111.6 minus 6.7-ish. I rounded a little bit, but it's going to look like that. So if you use the math for these phase angles and the magnitude, it'll come out as such. So for part B, we're going to do the same thing again. Convert everything to phasors and then solve. So B is 250 degrees minus 100 and then 150 degrees. Now you may be wondering why I'm not worried about the angular frequency omega. Omega is not changing. Their frequencies don't change like that. They can't really be changed mathematically. They have to be determined by some other factor. You can change the magnitude and phase of given frequencies if there was, say, a wave that was composed of different frequencies, right, with different magnitudes. Well, say if you only wanted these kind, or this one, you can make a circuit that'll pull out and attenuate everything else. Pull out the one you want and attenuate everything else. We call that a filter. You'll study that in linear circuits too, and other courses. So anyway, let's go ahead and get back to the beat of this. Go ahead and do the whole math thing that we did before. Get it up with 78.55 plus J66.6, which is going to translate to 103 and a phase angle of 40.3 degrees. Now you may be wondering, well, what is the physical significance of this? Well, we can transform it back into what it was before. We say the phase, or the angular frequency is 377 radians per second, and the phase is 40.3 degrees. There you go, that's back into the form before. This is a more complex form, or compact form. It makes the math a little bit easier too. I'll be right back. Sorry about that, I had an interruption. One more thing though. I forgot. When I was checking in my notes for this, I had it worked out on paper. It's 60 degrees. I remember before that sine of t, for example, would be cosine of t minus 90 degrees, or pi over 2. Well, since we want it to be just cosine to make it easier to work with, we do that phase shift. So 150 minus 90 is 60 degrees. But the answer is still correct. I just made a little mistake. Anyway, so we're going to do a similar thing for part C. We've got 80 phase angle, magnitude of 80, phase angle of 30. And then what's the second one? We've got 100 sine, so we're going to do minus 215, 225. So minus 225 is our phase angle. And the last one is 50 and a sine or a phase angle of minus 90. So now I've got all of this. Do the same steps we did before. Take the cosine of 30, multiply by 80. Take the sine of 30, multiply by 80j. Add up all of our numbers. We're going to end up with a complex number right around 140, and then 80 minus 80.7j, which is going to translate to 161.6, and in a phase angle of about 30 degrees. You could have rounding errors. I could have rounding errors. They all are not too big of a deal. Cosine, and it's 100 radian per second angular frequency, minus 30 degrees. And finally, part D. Once again, this one is interesting. We've got 250, it's same magnitude for each one, phase angle of 0, 250, then a phase angle of 120 degrees, and then a phase angle of, a magnitude of 250, and a phase angle of minus 120 degrees. Now this is kind of an interesting thing you may have not seen before. Well, remember earlier in the course when we did that whole delta y transformation? You can kind of see a reason why that happens in a moment. So if you go ahead and take the cosine and sine and all of these together, you're going to end up with 0 as your phasor, which means that all of these phases cancel each other out. They have the same average value. So if I had, let me write this. If I did, what is your cosine? So I'll say that this is 250, blah, 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 right? We've got one phase, and we've got another phase. I'm not drawing it very well, but I hope it helps you get the idea at least. But basically what happens here is that all of these phases are going to cancel out. Now the electricity is still there, or the voltage is still there, the currents are still there. But what happens is that if you have a 0 phase angle, say you wanted to supply more power to a very high power load, you had a really big motor, and you wanted to give it as much power as you could. Well, if you have 3 phases of electrical power, and they are in such a way that they are spaced 120 degrees apart from one another, then you don't need a return path for the current. You can just get away with connecting your load right here, to 3 wires. So you save a bunch of money on cabling, and all it really took was a phase shift. So that's the magic of 3-phase power. No return path is needed. Okay, so now we've got a little bit of math right here. And the problem is asking what the impedance seen by the sources and how many microseconds of phase is the current at a phase with the voltage. Well, this is where the magic of impedance becomes apparent. So you guys remember V equals I times R, your Ohm's law for resistance. Well, using impedance, we can generalize this expression and say that it's V equals I times Z. So you may remember when we were trying to find R Thevenin and R Norton, you did a ratio of a voltage and a current. You'd see that sometimes whenever you couldn't simplify the circuit into a resistor network because there's a dependent source. Well, you can do the same thing here. Z is going to be V divided by I, just like V over I. So, if we have VG, let's turn VG into a phasor to make the math easier. So 300 and then a phase angle of 78 degrees. IG, oh, let me make these capital because when we use a transform, we usually change the case to make it more clear. And let's see, 6 and then a phase angle of 123 degrees. Make that a better 6. Okay. So, to find our impedance, we're going to do VG divided by IG. So 378, 6, and a phase angle of 123. So, is it 123? Ah, yes. This is where I make that mistake again, with the sign. Sine is in quadrature with cosine, so we're just going to do 123 minus 90 degrees. That's going to be 53? No, 33. Okay, so this is going to be 33 degrees. Alright, so when we were doing this ratio, you may be confused, well, what do we do with the angles? I know how to do a ratio of whole numbers. Well, it's really simple. 300 divided by 6 is 50. And you do sort of like the phase of the numerator minus the phase of the denominator. So 50 is the magnitude, and our phase is going to be, let's say this is going to be phase of n minus the phase of d, our denominator. So 78 minus 33 is 45 degrees. So our phasor is going to be 50 and 45 degrees. This is going to be our impedance at this given frequency. Impedance is not constant. It does change with frequency. But at whatever frequency P given in the problem, that is our impedance, and it's measured in ohms. Now, basically this means that the current is lagging the voltage by 45 degrees. And that means that our load is primarily inductive. And we want to find out how many microseconds the current is out of phase with the voltage. Well, if we take our time, what is our frequency? Our angular frequency is 5,000. Okay. So omega is 5,000 radians per second. So if we divide all of this by let me say just the omega. Well, 45 degrees is going to be pi over 4 radian, and then it's 5,000 pi. You can also convert it, the 5,000 pi to degrees. Either way will work. So it's going to become 5,000 pi over 4. That's going to be 50 microseconds out of phase with the voltage. So if it's let's say that it's lagging by 50 microseconds. The current is lagging. Alright, so now we've got our first circuit. Let's say that we've got the current source IG, described in the problem, and it's in parallel with this 10 ohm resistor, which is also in parallel with this 50 microfarad capacitor, and then we've got an inductor and a resistor. This is 300 microhenry, yeah, 300 microhenry, and an 8 ohm resistor. Alright, and then IG is this. It is 922 cosine 2000 pi, or 2000 radians per second, plus with a phase angle of 30 degrees. So, drew the first thing was to draw the frequency domain equivalent circuit. And now we're going to find the voltage across the current source because of the source current and the phasor voltage. So, since we've got all these impedances, or since we've got all of these reactive elements, we've got 2 in fact, and 2 resistors. If we want to find out VG, the voltage right here, all you gotta do is combine all of these elements into one impedance, and then we'll be able to use basically Ohm's law. So number one thing I want to do, I want to write down the angular frequency, which we know is 20,000 radians per second. Then we're going to use the equation for the reactance of the capacitor, J omega C. It's going to be ZC, which in this case, omega is 20,000, and the capacitance is 5 microfarad. So doing all of this, we're going to get a reactance of J10 ohm from the capacitor. We're going to do a similar thing for the inductor. So our inductor has 300 microhenry times 20,000. It's going to become 20, or J6 ohms. So if we want to find the equivalent resistance, or the equivalent impedance, we're just going to look at the parallel and series combination here. So you've got 10 ohms in parallel with minus J 10 ohms in parallel with 8 ohms plus J6 in series. So if we simplify all of this, you just use, you can do the 1 over Z1, Z2, because whenever you're in the phasors and you're using impedances, you can use your series and parallel combinations for resistors to solve all of this. So I went ahead and solved this out on paper ahead of time. I ended up getting an impedance of 5.3 minus J 1.17 ohm. All of this together is ohm, which translates to a magnitude of 5.423 and a phase of minus 12.52 degrees. Now we've got an expression. We can get the expression for the IG. We don't care about the frequency. Magnitude is 922, phase is 30 degrees. So if we want to find out what VG is, we're going to do IG times the EQ. So that's 922, phase angle of 30 degrees, times 5.423, and a phase angle of minus 12.52 degrees. That works out to be VG equals 5,000 with a phase angle of 17.5. I got like 17.49, but it's close enough. So bringing that back into the time domain from the frequency domain, we can say VGT is the magnitude cosine of the angular frequency plus the phase angle volts. And that is the steady state expression for VT. That's our phasor voltage, and we've solved the problem. So now we're going to show that for a given frequency, or rather at a given frequency, not for all frequencies, the circuits in 9.18, figure 9.18, figure A and figure B have the same impedance between the terminals if the following conditions are met. So the way we're going to show that is we're going to say find the impedance of each one of these pieces. So ZA is an impedance of R1 in series with an impedance of J omega L1. And then ZB is going to be R2 in parallel with an impedance of J omega L2, which is going to translate. This is one time when I'm dealing with impedances, I like to use the other formula for parallel resistance, because it makes it a little bit easier to work with complex numbers, in my opinion. But either way will work. So R2 plus J omega L2. Now, if you sort of simplify the expression, we can get it into the form that is showing up at the top. And using a little bit of algebra, you know to get that ZB is going to be J omega R2 squared L2 plus omega squared R2 L2 squared divided by R2 squared plus omega squared L2 squared. And the reason why it's like that is because we were trying to get rid of J omega as much as we could to get the denominator into the same form. So once it's in that form, we can break it up into the real and imaginary part. So a real is going to be omega squared R2 L2. Actually, L2 squared. So I'll just say L2 squared divided by R2 squared plus omega squared L2 squared plus j omega R2 squared L2 over R2 squared plus omega squared L2 squared. So if we go ahead and compare the expressions we have at the beginning, the expression we have at the end, you can see that it is the ZB and R1, L1, they're the same at a given frequency, not every frequency, but a given one in this problem. And we're going to find out the same impedance for both of these. So let me go ahead and box this up real quickly just to emphasize. This is our impedance for R1. This is L1. So we can say it's L1, R1. That's how we can get the equivalence. So anyway, we're given an angular frequency of 4,000 radians per second. And let's see, the resistance, 5K ohms, that is our R2. And L2 is 1.25 Henry. So when I find out what values for L1 and R1 will result in the same impedance at this frequency. So what we're going to do is basically plug and chug. R1 is going to be 4,000 squared. So I'll just do it in scientific notation. 0.25 squared for L squared. And then 5.3. Let me write that again because that's kind of hard to see. That's 5,000. So we've got 5,000 squared, and then plus omega squared times L squared, so 1.25. Punch that into your calculator, and you'll get 2,500, which means 2.5 kilo ohms. And we do the same thing for L1. You're going to do 4,000 times 5,000 squared times 1.25 Henry divided by 5,000 squared plus 4,000 squared times 1.25 squared. Punch all of that into your calculator. I get 625 millihenry. That is L1. So at this particular frequency, they have the impedance the same as the 5 kilo ohm resistor in parallel with the 1.25 inductor. And if the frequency changes, obviously the impedance will change. So this is only true for 4,000 radians per second. So this problem is going to be similar to the last one. We've got equivalent impedance with capacitor and instead of an inductor this time. So ZA is going to be the resistance in series with the impedance of the capacitor. So it's going to be 1 over J omega C1. And ZB is going to be...
One sec.
No, not Siri. Sorry. It's going to be R2 in parallel with 1 over J omega C2. This is going to work out to R2 1 over J omega C1 or C2 over R2 plus J omega C2. So if we simplify that, we'll just multiply everything by j omega c2. I'm going to get the expression ZB is equal to R2 over R2 C2 j omega plus 1. And if we go ahead and take or multiply this by its complex conjugate, we're going to go ahead and do 1 minus R2 C2, I put a j over here, omega 1 minus j omega R2 C2. Multiply these all together, and you're going to get minus the j omegas on the bottom are going to cancel, and you're going to be left with R2 minus j omega C2 R2 squared, because we're multiplying R2 and multiplying it by R2 again. And then we're going to have 1 plus omega C2 squared R2 squared. Now, if you notice, we've got the same expression, or not the same expression, the same expression is going on around here. If you split up the fraction into the real and imaginary parts, you can get each individual impedance, which is what we're going to do next. So we're given an angular frequency of, let's see, 40 kiloradians per second with one. Okay, so R2 is given as 1K, and C2 is given as 50 nanofarad. Let me check. Yeah, 50 nanofarad. And our frequency, our angular frequency is 40,000 radians per second. So if we put all this together, R1 is going to be 1,000 divided by 1 plus 40,000 squared, 50 nanofarad squared times 1,000 squared. So if you punch all those numbers in, you get 1,000. 1 plus 4, so 1,000 over 5 is 200 ohm. And C1 is going to be 1 plus 40,000 squared times 50 nanofarad squared times 1,000 squared divided by 40,000 squared times 50 nanofarad squared times 1,000 squared. That's going to end up being 5 divided by 80 million. So that's going to be 0.0625 microfarad or 62.5 nanofarad. So this problem is kind of like our equivalent resistance circuits that we've seen a bunch of times, except this time we're dealing with impedances. And the problem asked for admittance, not impedance. Now, admittance is like the equivalent of conductance. Remember, if you had 1 over the resistance, that's going to be your conductance. It's not going to be C, but it's going to be, I believe the resistivity is written as rho. So if you had a resistivity rho, and then 1 over that is going to be sigma, your conductance. The complement here is going to be with admittance. Admittance is going to be 1 over Z. And basically it's how readily a circuit will conduct. Basically, if you have a high admittance, it'll let more current pass for a given voltage, kind of like Ohm's law at a given frequency. So basically we're just going to find the equivalent impedance, and then we're going to take its reciprocal and use that to give the answer to the question. So this is very helpful for a time where it's very helpful to have a calculator that can do complex numbers. In my case, I can. So instead of doing it step by step, since we've done these so many times, I think we can kind of combine elements. So we're going to have those two added, and then we're going to put all these in parallel, and we're going to add them all up. Because with impedances, you can treat them kind of like resistance. Because really that's what they are. They are resistances that depend on frequency. And we're not given a frequency here, but we're given the impedance, which means that would say that this whole circuit, that capacitor at this frequency has minus J omega, 2 omega, or J2 ohms, not omega. It is omega, but different omega. Anyway, so I'm going to add I'll start from A. So J 12.8 ohm. Then we're going to do 1 over 6 minus J2 plus 1 over 4 plus J12 plus 1 over 5 plus 1 over J10. So minus 1, that's going to be our parallel equivalency. Oops, not equals. Plus 13.6 equals ZAB. So if we simplify the middle expression, J12.8 plus, let's see, 0.375 minus J 0.125 to the minus 1 plus 13.6. Now, you take the reciprocal of this, we're going to get 2.4 plus J 0.8. So if we add all these numbers up, so let me go ahead and just write it one more time. J 12.8 plus 13.6, we get 16 minus 12J ohm at this particular frequency. So that is our impedance, ZAB. And to find the admittance, all I gotta do is 1 over ZAB. So I'm going to do 1 over 16 minus 12J. Let me write that out better. 16 minus 12J. That's going to be 0.04 plus J 0.03, and Siemens or Mohs. You may have seen those before. They're kind of like a deprecated unit. In SI, 1 over an ohm is Siemens. I think I spelled that correctly. I might have flipped the I and the E. Anyway, so we've got, if you turn these into millisiemens, that's going to be 40 millisiemens. I'll do it to the unit at the end. 40 plus 30 J millisiemens, not milliseconds. That's why I use a big S. I think there's one more part of this problem. Let me double check. Oh yeah, express Y, A, B, the admittance in polar and rectangular form. Well, we already have it in rectangular form. So if we want to turn it into a polar form, all we got to do is find the magnitude and the angle. So 40, incidentally this is a 3, 4, 5 triangle, so let's go ahead and just write it all out. Here's, is it 30? No, this is 40. 30, then 50. I kind of gave away the ghost, but if you remember, 3, 4, 5 triangle. There's that. And then the phase angle. It's not really a phase angle. I mean, it is, but I don't want to say that. It's going to be the tangent inverse of 30 over 40, which is 36.87 degrees. So we can say that the magnitude is 50 and the phase is 36.87 degrees. And this will be still in Siemens. It's just this time I wrote it as a phasor. So this time we're going to do the impedance, which is, like I said, just like resistors. We add up impedances and everything using the same rules of that resistors. We do with resistors, I should say. So let's get right to it. I'll start with A. So 1 minus J8, and then plus, let's do the parallel combinations now. So 1 over 2 plus J4 plus 1 over 10 minus J20, so minus 1 plus 1 over 40 in parallel with 1 over J20 minus 1. And then that is all over math stuff. So this will simplify down to 3 plus J4. And this will simplify down to 8 plus J16. So if we add up the remaining bits, we're going to get ZAB equals 12 plus J12 ohms. Like I said before, it's a lot easier if your calculator can do complex numbers. Otherwise, you'll be here doing complex conjugates all day. But you'll be able to do it by hand if you're persistent. So also, we have to express it in polar and rectangular form. Well, this is pretty easy. It's like before where we had the 3, 4, 5 triangle. This time we have a 45, 45, 90. So we don't really have to do any math. This is obviously going to be root 2 times whatever x is. So 12 root 2, what does that look like? 12 times the square root of 2. It's like let's say 16, 17. So we'll say that the magnitude is 17 and the angle is going to be 45 degrees. So we'll say that ZAB is 17, a phase angle of 45 degrees. It may be a little bit off, but it's just within the realm. And if you want to be more thorough, basically all we have to do is say, okay, well, 12 squared plus 12 squared is what? Whatever square root 288 is. And the tangent inverse of, sorry, not 45, that's the result, of 12 divided by 12, tangent inverse of 1 is 45 degrees. So this one's pretty simple. This problem, we've got a circuit, and we've got to find out where the impedance ZAB is purely resistive. Now, that doesn't mean the frequency at which the inductor and the capacitor, the reactances cancel out, so much as it does the phase angle of the impedance has to be 0. So we're looking for where the impedance ZAB has a magnitude but 0 phase. And we'll find out the magnitude later, which is the value ZAB. Anyway, so to do this, we need to find the impedance of the inductor and the capacitor. So inductor is going to be J omega L. So L is 160, not microhenry, nanohenry, yeah, microhenry. 160 microhenry ohm, and ZC is going to be 1 over J omega 25 nanofarad. So that's going to be, let me get my calculator. Okay, so I'll just keep the J at the bottom for now. Well, we want to make it a little bit easier to rationalize later, so I'll go ahead and bring the J up, make this minus J times 40 million divided by omega. And this is a series and parallel network, so we're going to have ZL in series with the parallel combination of R and ZC. So we're going to have ZAB 160 J omega and minus 40 million over omega times 100 divided by, then put together as we adding, you add negative number, so that we subtract 40 million divided by omega. So I'm going to multiply everything here by omega to simplify. And it's going to make it ZAB is 160 J omega plus minus 40 times 100. Let's see. it's going to be 40 minus 40 E8 omega. Or not omega. Omega is going to go away. Minus 40 E8. Actually, yeah, okay. This would be 48 divided by 100 omega minus J 40 million. Okay. So if we multiply everything here, let me divide all this by 100 just to make it easier, because we're going to do the complex conjugate. So let me think. Divide this down, this will become just omega, and then this becomes 40,000. This becomes, actually this doesn't change, does it? No, it shouldn't change. It should still be a million. So this is just going to become 1. Basically just divide the denominator by 100 to get into an easier form for the complex conjugate. So 1 plus J 40,000 40,000. Okay. Multiply everything out here. Denominator is going to cancel, so this is going to become ZAB is, let me get this in the correct form. Plus 40 times that. Okay, so we're going to be 40 times 40 times 10 billion. Okay, so I get answer of 1.6 E10, or not E10, E13. That's over, or minus the J omega 40 million, all over omega squared plus 1.6 times 10 to the 11th power. So that's everything. 160 billion. Okay. Now, like I said before, if our impedance is purely resistive, basically that means that the imaginary parts right here are going to cancel out. So what we want to do is we want to pretend that this doesn't exist when we solve for the frequency. So to do that, we're going to just say J omega. I'll just write this 1.6 E minus 4 plus J omega 40 million divided by omega squared plus 1.6 11. And all of this equals 0. And it has to equal 0 for it to be purely resistive, because otherwise there will be a non-zero phase angle, which means we will have some reactance in the impedance. So let's think. If I multiply, well, we don't really care about the J anymore, because we're worried about frequency, and J is the thing. So we're just thinking about frequency. Well, we got omega here and omega here, so cancel these out. I'll just say that this is 1.6 e minus 4 plus, oh, I'm sorry, forgot the minus. So I'm gonna put the minus 40 e, this 40 million omega squared plus 1.6 11. I'm just trying to simplify all this out. So that's going to be something like omega squared plus 1.6. Let's see, to minus 4. That's going to be T11. And then minus 2.5 11 equals 0. Okay. So if I simplify that, so omega squared plus 1.6 minus 2.5 is 0.9, I think. Yeah, so 0.9. So this is going to become minus 0.9 E11 equals 0, which means omega equals the square root of 0.9 E11. The square root of 0.9 let me just write it like this. So 9 E10. That's going to become 3 E5. So 300,000. I believe it's radian in this. Yeah, because we're in phasor. So radian per second. So that is going to be the frequency where the phase angle of the impedance is 0. That's where we're purely resistive. So if we go ahead and plug that frequency in for our expression for the impedance, let's go ahead and punch. We don't really care about the real part because the imaginary part's going to cancel. So if I say 1.6 E13, E13 divided by 3E5 squared, and then plus 1.6 E11. That is going to be, let's see, 1.6 E13 divided by 3E 9E10 plus 1.6 E11. Okay, I get 64 ohms as the impedance at that frequency. So, yeah. And the phase angle is going to be 0 because we have no, once I said it was pure resistive, we have no phase angle because we made sure that the frequency was where it canceled out.